Right, so hi, my name is Duncan. I was obviously on the HSMA 5 course. I've been an analyst, so just a bit of background, been an analyst in the NHS for some time. Although my only real background in coding and so on was in SQL, so I was quite well versed in SQL, and just basic sort of BI reporting, but I've not really done anything with Python or anything of that kind of programming of that kind. So my project, the organisation I work for, we were supporting the Northwest Neonatal Operational Delivery Network in undergoing a change program to look at service allocation and distribution within the Northwest. So we were supporting them just from a sort of straightforward BI data in, data out perspective, but I saw it as an opportunity whereby we could implement some of this more complex, more useful sort of scientific approach to data that we'd learned on the course and use it for my project piece. So with resource allocation modeling, you can quickly run into a permutations problem whereby when you have a significant number of sites and you have a significant number of source locations, that acts as a kind of multiplicatory factor. And you suddenly run into an incredibly large numbers of possibilities of different options that you could calculate, basically more than you could feasibly calculate with current sort of computing resources. And so to sort of brute force calculate every different possibility of sending this person to this site or this person to that site, and then modeling that and seeing how it goes, it basically becomes impossible. So one of the strategies that we looked at on the course was how you could evolve a solution out of possible solutions and then work towards a good outcome. It may not be the best side out of all of the possibilities, but good enough based on your objectives. Another thing this is also really good for is multiple objectives. So if you're basically not just looking to reduce travel time, you might also be looking to make sure that there are enough people going to particular sites so that you can recruit the right level of specialty clinicians and keep them employed in those regions. So just sending everyone to their nearest site isn't necessarily the best approach, and we have multiple competing objectives. So the evolutionary algorithm enables us to manage those multiple objectives and then work those towards a good outcome for all of the objectives that you're looking at. So the data that I fed into the algorithm was BadgerNet data, which is the neonatal critical care clinical database. So I've had access to that data from the region, and that's the data that I've fed into the algorithm. So when I first started the project, I had a bit of a chat with one of the members of the Pencord team, and he pointed me towards a piece of work that he'd been involved in, which was a framework to address the key issues of the neonatal service configuration in England. And so I've kind of copied the approach from that into the model and used the objectives that were laid out in that approach with a couple of small tweaks based on the things that they're concerned about in this particular instance. And those are those objectives there. So a couple of them that stand out, obviously minimizing the average travel time, maximizing the proportion of people that are within 30 minutes from any site, minimizing the maximum distance, but also maximizing the number of people whose activity takes place in one of the level 3 sites, so one of the larger sites, whereby obviously we can ensure that we've appointed clinicians with the appropriate specialist knowledge and also the equipment that they're going to need as well. So obviously, as I've said, we're not looking at just solving nearest site. We've got multiple. That would be nice and easy. but unfortunately the real world isn't nice and easy. So using calculated travel times rather than crowfly's distance. I know the graph there looks like crowfly's distance, but that's just how I've displayed it. So using real world actual travel times, we've basically modeled the data. So in an evolutionary algorithm, the site assignments are initially done at random, and then in order to evaluate the individuals, so we have a population of individuals that are then modified and literally sort of, you end up using the language of evolution very quickly and very naturally with this, because you literally crossbreed solutions, and solutions carry over into the next generation of the iteration. So it will test each individual in the population and then breed good ones out of an algorithm that we write that's to measure your fitness objectives. Essentially, you're testing how well the population performs against the objectives that you set out in the initial criteria. So you evolve solutions over time and test each individual in that generation and try and drive the evolution towards better and better solutions in each generation. So it evolves a set of solutions which are obviously not perfect, but they are good solutions towards the objectives that you're setting out. A good way to kind of visualize this is the competing objectives is along something called the Pareto front. So if you can see on the graph on the left there, you can immediately see how one objective improving the measure on one objective can degrade the measure of another objective. So a good example of that is where we want to minimize the travel time, but obviously maximize the size of the sites. So you can see how those objectives compete with each other, and to improve one will inherently degrade another. And what we look for is solutions across something called the Pareto front. And that's really difficult to visualize if we've got more than 2 or 3 objectives. But these graphs should give you an idea of how those populations of solutions exist in what is called the solution space. And we are basically looking for one that satisfies all of our objectives well, rather than the best possible one. And you can also create some really exciting looking individuals here where we can see how those populations are actually evolving. They're kind of little use to the actual output, but they are interesting to sort of watch how your populations are actually evolving over time. So once we've modeled those, and again, you sort of mirroring the same approach as was used in the sort of source paper, I've also built a discrete event model that simulates the flow of patients through a neonatal critical care unit. Obviously, they can flow through the different levels of care in a kind of unique manner, but that's because obviously very young babies can get well very quickly, or they can deteriorate in their condition very quickly. So they can jump from any level of care, or then be discharged straight from intensive care, and so it's kind of a complex system. We've also included in that model the fact that, say, a free neonatal sort of intensive care bed, whilst free, can also handle the care of a baby requiring level 2 care. So that's a free resource. So it's kind of a complex model that enables those resources to be used in quite a complicated way. But what that enables us to do is to test those scenarios. So once we've generated a good individual solution in our evolutionary population that may suggest that we have, say, 2 beds of this type in one particular region, 2 beds of another type in the same hospital, we can then look at how many admissions that facility is seeing through the maternity unit, and then model things like average sort of queuing time to the bed weights, and the actual usage of those resources over time, just as a kind of fail-safe to kind of double check that the outputs from the evolutionary algorithm aren't suggesting something that's going to run us into problems down the line. And I've also looked at putting that into a Streamlit web app so that the commissioners can use that to inform their decision making as well. So by plugging in those numbers and looking at the birth rates in those units, we can actually have a look at the how the units are actually going to perform with those different makeup of bed types. So at the moment, we're at the stage of kind of working through different solutions. So those different solutions may be where things that the commissioners already have in mind from a clinical perspective, which might be to reduce activity on a certain unit and see how that activity then flows into other spaces. So we can do that by sort of modifying the input data, adding new different constraints and parameters on to the evolutionary model, and then testing the fitness again of a whole new evolution of solutions and seeing where that activity goes. So at the moment, we're working with the commissioners to model those different scenarios and put that into a dashboard for them, which displays the data from those models back to them in a way that kind of matches the data that they're used to seeing as well. So we have fed that into essentially a proprietary dashboard solution there, but it is what they're used to seeing, and I think that will help aid the understanding of the dashboard too. Of the data, sorry. So yeah, I think that's me. So